Hello, and welcome to another edition of Advanced Projects for the Arduino using the Uno Pro Logic. In this video, I will show you how to create a fast Arduino oscilloscope using the Arduino Uno with the Arduino Oscilloscope code and Uno Pro Logic and a simple C# application running on the PC. This project can be built for less than $60, and all the code is open source and freely available at www.earthpeopletechnology.com. All of the software applications are free and can be obtained over the internet. For this video, we connect our Uno Pro Logic to a laboratory function generator to provide an analog signal to capture with the fast Arduino oscilloscope. We use a plus 5 volt DC power supply to provide a trigger threshold level. Starting the oscilloscope is just to click on the application file in the project folder CD. Then select the EPT device in the drop-down box, click the Open button, click on the Start button, then select the On-Off button on the scope is displaying the analog signal. Here, the function generator is providing a sweep of sine waves from 10 Hz to 250 Hz. Next, we'll set the function generator to produce a 1 kHz sine wave with a 4.5 volt amplitude. So to do this, just click on the function generator and select 1 kHz. And select the amplitude and dial in 4.5 volts. For the trigger level input, we use this lap supply. We're going to set this supply to 3 volt DC signal. This will give us a DC threshold which the analog signal must cross in order for the scope to display the waveform. The EPT Fast Arduino Oscilloscope has the same functionality as a full-featured scope. These features include the trigger settings, rising, falling, toggle, horizontal time-based selection, vertical scaling, voltage amplitude scaling. Grab the slider and you can scale the voltage up or down. Time scaling. The slider lets you zoom into the signal to see details. Now, most of these features are implemented with sliders. The sliders make it easy to select from multiple views. Once the value is selected by the slider, an underlying event in the C# code causes the Uno Pro Logic to transmit a command and the value to the Arduino code. The fast Arduino scope does have its limitations. It is most notably limited by the ATmega 328 microcontroller. The chip uses an ADC, which we select the 8-bit mode to increase the throughput speed. In the block diagram of the internal ADC circuit of the 328 microcontroller, we can see the circuit functionality. The source 1 input is from our analog signal to be displayed. The signal is selected by a multiplexer and is directly applied to the conversion logic. This logic is directly controlled by the ADC clock. Changing this clock value changes the amount of time between conversions, and it ultimately controls how fast of a signal can be applied at the analog input. The ADC has 8 selectable clock inputs to drive the conversion of analog to digital. The horizontal slider controls which of the prescaler values is to be selected. These values determine what the ADC clock frequency is. Now these frequencies are 125 kilohertz, all the way up to 16 megahertz. The ADC is not designed to handle frequencies above 1 megahertz. Now this can be seen in the graph of the effective number of bits versus the ADC clock. You can see from the graph that the resolution deteriorates to less than 8 bits at frequencies above 1 megahertz. This is also seen as aliasing. So we will keep the ADC input frequency to 1 megahertz or less. As you can see on the screen, the EPT Fast Arduino Oscilloscope has 9 divisions in the horizontal direction and 9 divisions in the vertical. Grab the horizontal time-based slider and pull it to the right to decrease the time per division. This allows us to scale into the wavelength of the input signal by changing the ADC clock. This reduces the time between conversions and lets us see faster signals at the analog input. There are 450 samples that are displayed in the window. This results in 50 samples per division. Divide the selected ADC clock frequency by 1 and multiply by 13 clocks per conversion, then multiply by 50 samples per division to arrive at the time per division. If we choose 1 megahertz for the ADC clock and perform the same calculation, we arrive at 650 microseconds per division. This can adequately examine 3 kilohertz signal at the analog input. Examining the scope performance, I can move the position of the waveform in the window using the X position slider. Use the voltage scale slider to give a boost to small voltage signals so we can see them better. Use the vertical position slider to reposition the waveform for better viewing. There are also other user controls to select the voltage reference, the AREF, AVCC, or internal reference voltage. Now I will dial the function generator up to 3 kilohertz sine wave. The horizontal time-based slider has selected 650 microseconds per division. Here we can see about 5 complete periods of the wave. I'll grab the time scale slider and we can zoom into the 3 kilohertz wave. Now we can see more details of the wave here. And next I will set the function generator up for a sweep. This will slowly increase the frequency from 100 Hz to 3 kilohertz. You can see that the changing the signal from the function generator immediately shows up on the EPT Fast oscilloscope. It shows the high performance of the oscilloscope. Next I'll decrease the time scale so we can see more cycles of the 3 kilohertz wave. And now I'll set the function generator to produce a pulse which repeats every second. The pulse duration is 10 milliseconds. can see the pulse on screen is 10 milliseconds based on the horizontal time base. Next, I'll change the pulse duration to 20 milliseconds. And 25 milliseconds. And this is just showing the performance of the scope and how fast it follows the change in the input. Next, I'll set the function generator up to output random noise. And the amplitude is 1.7 volts RMS. So, you can see that the EPT Fast Arduino Oscilloscope has high performance. Next, let's look at the equipment needed for this project. So the equipment needed to build this EPT Arduino Oscilloscope is the following. An EPT Uno Pro Logic, an Arduino Uno, USB Type A cable, the solid core wire, the plus 5 volt variable power supply with cables, and the function generator with cables. Next up is a description of the hardware needed for the oscilloscope. The Arduino uses the analog comparator to trigger the scope. The ADC then samples the analog channel 0. The samples are stored in a buffer in the SRAM. Because of the method of using the Arduino hardware to behave as an oscilloscope, we have to build some hardware. The analog signal must be applied to both the analog channel 0 and the input to the analog comparator. To do this, connect the Uno Pro logic to the Uno. Next, connect up the positive 5 volt variable power supply. Connect the ground pin to pin 6 of J12 of the Uno Pro logic. Connect the positive lead of the power supply to digital input 7, pin 8 of J8. Next, connect the ground lead of the function generator to pin 7 of J12. Now we need to build a cable that connects the signal to be displayed to analog input 0, which is pin 1 of J9 of the Uno Pro logic, and to digital input 6, which is pin 7 of J8 of the Uno Pro logic. Finally, connect up the positive lead of the function generator to the Y cable that we just built. And this will connect up the input signal to analog input 0 and the comparator input. Next up is the Dataflow Discussion. The Fast Arduino Oscilloscope is controlled by the C# application. After applying power and opening up the Uno Pro logic, use the button events to send commands to the Arduino to perform selected functions such as starting the display, changing the trigger polarity, voltage reference, etc. Use the sliders to select new values for the horizontal time base, time scale, vertical scale, etc. The data flow for the fast oscilloscope consists of the Arduino Code, the Uno Pro logic code, and the C# window code. When the Arduino powers up, it initializes the ports, variables, and registers. Once the Uno Pro logic has been started, the on button from the C# application button will send the start ADC command to the Arduino Code. When the start ADC command is received and decoded, the Arduino Code automatically calls the start ADC function and the start analog comparator function. The first of these functions turns on the ADC and causes the ADC to convert whatever is on its analog input into a digital word. When this conversion is complete, an interrupt function is called the ISR ADC underscore vect. When this happens, the loop function is stopped and the interrupt function executes. It examines if the trigger bit has been set. If it is not, then the update variable is set to true and the interrupt exits. When the interrupt is complete, the loop function continues with the next instruction. It will eventually check if the update variable has been set. If so, the value of the ADC conversion is stored in the ADC buffer, and the buffer array index is incremented. The ADC has been configured to continuously start a new conversion on the completion of the previous conversion. This process repeats until the analog comparator has sensed the input to the analog channel has breached the threshold level. This is the trigger threshold level and is set by applying an analog voltage at pin 8 of the J8 connector. So the pin 8 of the J8 connector is attached to the internal analog comparator inside of the AT Mega 328 chip. It is connected to the negative input of the comparator. The positive input of the comparator is connected to pin 7 of the J8 connector on the Uno Pro logic. The Fast Arduino Oscilloscope cable harness connects pin 7 of J8 to pin 1 of J9. This is the attachment for the analog signal to be displayed on the oscilloscope, and in our case is attached directly to the function generator. When the analog input signal on the positive input of the comparator is greater than the input on the negative input to the comparator, an interrupt is called. Now this interrupt is the ISR analog comparator vector. The loop function will exit and start execution of the first instruction in the comparator interrupt vector. The first thing to do is to turn off the analog comparator interrupt so that no following comparator interrupts can disrupt the process. Next, the wait variable is set to true. The stop index is set to the current count of the ADC counter plus an additional number of counts set by a variable called wait duration. These extra counts will allow a full cycle of the analog input signal to be captured into the ADC buffer and eventually displayed. Finally, the value trigger count is set to the ADC counter, and this will be used when transmitting the ADC buffer to the Uno Pro logic. When the ADC buffer has completed transmission, the Arduino Code asserts the end of buffer signal. This signal is used to create the trigger 2 in the active trigger end term inside of the Uno Pro logic. After that, reset the trigger variables and restart the ADC and continue on with the loop function. During each cycle of the loop function, the serial port is checked to see if a new command has arrived at the C# application. If a new command has arrived, the Arduino Code will break and perform the selected command. Okay, next up is the Uno Pro logic functionality. The CPLD does not need any initialization as the device is ready to operate as soon as the power is applied. The data flow in the Uno Pro logic starts with the wait loop for the start-stop control signal to be asserted from the control register. Once this happens, the data flow will fall into the wait loop for the write enable. When the write enable from the Arduino asserts, it causes the block of code that writes bytes into the local FIFO, the Uno Pro logic, to read the data on ports B and C, then clock that byte into the FIFO. This process continues until the internal FIFO count reaches 8 bytes. When this happens, the FIFO full flag is set. When the FIFO full flag is asserted, the state machine leaves the idle state and enters the store FIFO count state. In this state, the FIFO out count signal is updated with the full count of the FIFO. The state machine will immediately enter the start send block state and asserts the block out send signal, which informs the active block end term that a block transfer has started. The state will wait for the block busy signal to assert, which is an acknowledgement that the block transfer has been accepted by the active transfer library. Next, the FIFO high state is entered. In this state, active block end term toggles the block byte ready signal to inform the user code to put a new byte in the block out byte. This user code will toggle the FIFO read enable signal to push the first byte in the FIFO onto the blockout byte. The state machine will then cycle to the FIFO low state. In this state, the state machine will wait for the active transfer library to complete the transfer across the USB. When the transfer is complete, the block byte ready signal goes low and causes the state machine to go to the increment count state. In this state, the blockout flag is checked for assertion. If it is asserted, the state machine goes back to the FIFO high state to wait for block byte ready to signal that the active block end term is ready for the next byte from the FIFO. If the blockout flag is not asserted in the increment count state, then the blockout counter is checked to determine if the count has surpassed the FIFO out count. If the statement is true, the state machine goes to the block send complete state. When the block busy signal deasserts, the state machine goes back into the idle state. The data flow waits in a loop for the FIFO full flag to assert and again start the process over again. Next up is the C# window functionality. The C# data flow on the PC starts with the initialization of variables, controls, events, and read callback functions. The Windows form is displayed on the PC, and the system registry is scanned for any Earth People technology devices. Any devices that are found are added to the drop-down box. The user must then select the available EPT device and click on the Open control. This will select the device and allocate all memory needed for the active host end terms. Next, the user must click on the Start button. Clicking this button will send the start-stop bit of the control register to the UNO Pro logic. The CPLD will decode this message and assert the start-stop control signal internally. Once this signal is asserted, the user must click the on-off button to send a serial command to the Arduino. This is the Start ADC command. This causes the Arduino Code to start filling up the ADC buffer with samples from the ADC conversion. When the Arduino Code has detected a trigger and filled up the ADC count has reached its max wait duration, it transmits all bytes in the ADC buffer up to 500 bytes to the UNO Pro logic. Each byte is transmitted through the active block end term of the CPLD code. When the blocks are received by the C# window, the read callback function is called. The read callback will call the EPT parse receive function, which calls the transfer out receive function. In this function, each byte is stored into an internal byte array called scope buffer. This process of filling the scope buffer array continues until the Arduino Code has sent its entire ADC buffer up to the C# window. When the Arduino Code has completed the transmission of the entire ADC buffer, it asserts the end of buffer signal. Now this signal is connected directly to pin 3 of J9 of the UNO Pro logic. The CPLD uses this signal to send a trigger 2 using an active trigger end term. This trigger 2 is received by the C# window. At this point, the scope buffer has a complete cycle of the analog signal to display in its window. The trigger 2 active trigger end term causes the invalidate function to be called inside of the code. This function will automatically cause the functions with a graphics variable to be refreshed. During the refresh of the display data, the vertical and horizontal scaling is performed. Next, redrawing the graphics will cause the new values in the scope buffer to be displayed in the oscilloscope window. Finally, all of this data is displayed to the screen. This cycle repeats until the stop button is pressed. Now, the button events will cause code to be executed when a button is pressed. The Visual.net framework takes care of all the background code which monitors the button events and any interrupts associated with executing the code. What we need to do is just add in what we want to do when the button is pressed. So, this video has given you an introduction to the EPT Fast Arduino Oscilloscope. All the code is open source and available at www.earthpeopletechnology.com under the resource banner. Please download the zip file and work through the project and post any comments to the forum page. Thanks for tuning in.
Come